Good day, everyone. Now, there is a specific concept in electricity that we have to speak on, all right? And that concept is what we call drift velocity. Now, the objectives are there on the board. It says we should explain drift velocity in terms of charge carriers, right? The syllabus requires for us to derive an equation for current in terms of drift velocity, where n is referred to as the charge density, and they also want us to be able to can use this equation to solve problems. So in order for us to do this, guys, we have to look at a specific conductor. So if we have a piece of conductor, right, we know that most conductors, if you were supposed to cut it in small pieces, you would get small chunks of a cylinder. Now, each cylinder has a cross-sectional area, which we can look at here, right? And that specific conductor will also have a length of L. We can call the cross-sectional area A, and we know that inside of this conductor there are numbers of electrons, so to speak, and in order for us to find out the number of electrons, we will have to look at the fact that there is a variable which we call n, and that variable n is the charge density. And what the charge density tells us is the number of free electrons that are inside of that piece of conductor divided by the volume of the conductor. So this is what n signifies. Just like how when you have density in real life, right? Density is mass upon volume. Whenever we're dealing with electronics or electricity, so to speak, and we're talking about charge density, it's the number of free electrons divided by the volume. Now, when we're dealing with volume in terms of a cylinder, we divide by the length of the cylinder. The volume rather of the conductor will be given as the area times the length. So we know that information from the fact that we know that the number of free electrons divided by the volume is given by n, the charge density. If I wanted to find the number of free electrons, I would transpose my equation. When I transpose my equation, I get n, which represents charge density, times the volume, or I could say n times the area times the length. Now, with that being said, in this piece of conductor, since there are electrons inside of this conductor, we expect that each electron will carry a charge, and we want to know the total charge of these electrons. So in order for us to find that, I would have to now know the amount of electrons firstly and the charge of the electron. So the number of electrons, as was stated above, is given by n times a times L, and the charge of an electron is E, right? And E, we know that as 1.6 times 10 to the minus 19 coulombs. Now guys, whenever we apply a power source to the piece of conductor, we expect that electrons are going to flow from this end of the conductor to this end. And with that being said, we expect that the electrons, or the charge rather, that is flowing is going to move from this end of the conductor to the next end. And we can see that the charge move L distance, all right? we're putting in the parameters now of the conductor. So, but in addition to that, it also traveled a specific time. Good. So from where the conductor starts, from here to where it ends, it there's a time that is associated with it. Now, whenever we measure, whenever we know the the distance that a moving object travels and the time that it takes, we can now put together those quantities and we can get what we call the speed of the electron, or in some cases we can say the drift velocity of the electron. So with that being said, we can go ahead and write this formula right here that says v, which stands for velocity, is equal to L, which is the distance or the length divided by the time that the electron took to move from one point to another. So that's how we would find the overall velocity of the electron as it moves through the conductor, right? So with that being said, guys, remember we want to derive an equation, good, for I. So we have to go back to the fundamental equation that speaks on to say that I, or current rather, is the rate of flow of charge. Good. So at this point here, we know the total number of free electrons. We know the total charge of the free electrons, and that is given by L times E. So we can go ahead and substitute that in our equation. So this is what I did here, and I now have N times A times L times E, all of that divided by the time that it takes. Now we have not yet completed our derivation of this this thing. So we now have to involve we now have to find a way to get rid of time that is in the denominator here, or find some other way of defining time. And from our velocity equation, we can simply do some manipulation or transposition to make time become the subject. And when we do that, we get an equation that says T is equal to L over V. That this is what you're looking at here. And we can now go ahead and substitute that into our equation. So we're left with this equation to say I is equal to N times A times L times E, all of that divided by T, which is L divided by V. Clearly, we can cancel out L, because L is in the numerator here and it's also in the denominator. So what we're left with is N times A times E divided by 1 upon the speed. Good? Or we can call it velocity. By our mathematics, we can simply find the reciprocal of that, and the reciprocal would give us that equation that we wanted to find, to say that current can also be calculated, or you can find the current in terms of drift velocity and the area. Okay, so this is what we're left with, to say that I is equal to N, which is the charge density, times the area times the charge of the electron, multiply by the velocity electrons. And to transpose for velocity or drift velocity, we would take this here and divide it on this side. So easy transposition. So all of what is here divided by time. So this is what we're left with, to say V is equal to I divided by N times A times E. Alright? So always remember, once you remember how to do this derivation, right? then you are way on your way to solving these problems, so to speak. All right, guys. And here I have a little bit of information, some notes that you can look at to understand that, when charges is flowing through a conductor, we expect that, there's going to be some amount of collisions by virtue of the particles that are inside of the conductor, right? And we can expect that the electron will gain some amount of kinetic energy, and it's that kinetic energy. If we remember how kinetic energy is defined, half mv squared. So velocity is involved in that equation, right? And that's the velocity here that we are basically trying to find, so to speak. That overall velocity of the electrons as they move and so forth. All right. Yeah, man. Now let's look at a practice question, right? Now here's a question to say that a copper wire has 8.5 times 10 to the 28 charge carriers, free electron, meters per, what would I say, meters to the minus 3, and the wire has a current of 2 amps, and it also has a cross-sectional area of 1.2 millimeters squared. They say calculate the average drift speed of the electrons. So we know which equation we're going to use already. Equation says I divided by NA upon E, and we can now plug in our values. So we know the current, which is 2. We know the N value, which is our charge density, multiplied by the area. Now guys, we have to understand that we have to put our measurements in SI units. So that's why I had to convert millimeters into times 10 to the minus 3. And we have to also understand that all of that is being squared, because this thing is being squared. All right. When we're dealing with area, the units is squared as well. So we have times 10 to the minus 3 times m, all of that squared, times the E value, which is charge of an electron, which is 1.6 times 10 to the minus 19. When I put the denominator in my calculator and squaring, well, whenever we're doing this part here, we're dealing with powers. Power to power, we multiply. All right, so that's how we get minus 6 when you put it in your calculator. So we get a minus 6 right here, and we put all of this in our calculator. We end up with 2 divided by 16,320. Whenever I do my final calculations, I get a 1.23 times 10 to the minus 4. And clearly, because we are dealing with velocity, we expect that it is going to be meters per second. All right, so that's an easy problem for us to attempt. Now let us go ahead and try this problem for ourselves. Okay, it says that the average drift velocity in a metal wire is 6.4 times 10 to the minus 4 meters per second when the current is 0.8 amps. The area of the wire is 0.5 millimeters. I mean, my apologies, not area. The diameter of the wire is 0.5 millimeters. And they say calculate the number of free electrons per unit volume in the wire. So we expect that we're finding the N value. So let's just go ahead and attempt this question. So we know V is 6.5 times 10 to the minus 4 meters per second. Then we know A, which is our we know I rather. We know I, So we know that I is equal to 0.8 amps. Now we know the diameter of the wire, which is 0.5 millimeters. What else do we know? We don't know nothing else for now. Alright, so they want us to find N. So one of the things we have to do first is to find the area. So area of wire is given by this formula to say that pi d squared divided by 4, or you could say pi r squared, but because we know the diameter value already, we're just going to use that. So pi is 3.14 times the diameter, which is 0.5 times 10 to the minus 3. Minus 3 comes from this, millimeters. All of that is squared. Good. And divided by the 4. So if we go ahead and put that in our calculators, we should be getting some values here to say that so good. So our area is given to us as 1.96 times 10 to the minus 7 meters squared, because we're dealing with area, correct? Having said that, now let's go back to our equation that says what are we trying to find? We're trying to find N, so we can say I is equal to N times A times E times V, and we can just take this A, E, V and divide it on both sides, seeing that it's multiplying on that side, so A times E times V. So with us doing that, we are left with N. N is, this would cancel out, so I divided by A, E times that. So we know I rather, which is 0.8 divided by the area, which we just calculated to be 1.96 times 10 to the minus 7. That multiplied by charge of an electron, 1.6 times 10 to the minus 19, times the velocity, which was given to us as 6.5 times 10 to the minus 4 meters per second. All of that is being divided here. So let's go ahead, put that in our calculators and see what answer we are getting. So when I put the denominator in the calculator, N, so 0.8 divided by 2.0384 times 10 to the minus 8. Right, divide all of that. So the 0.8 divided by that 384 times 10 to the minus 29 rather. So it's actually 29 and not 28. 29. I get a value to say that N is equal to 3.92 rather, times 10 to the 28. And this, the unit here is meter per meter. Wait, let me see if I can say it properly. Per meter cube, I believe is what we would call it, per meter cube, or you can say meter to the -3. Yeah, so that's the unit for that. So that's what you would do, guys. So know how to derive that equation, know how to can solve problems, know what N stands for, charge density, and it is basically the number of free electrons divided by the volume. Alright, so this is where we're about to stop for today. Right, if you have any questions, let me know and we can take it from there.